There is another way to verify calibration quality. Not every calibration algorithm enables us the self-verification procedures. So as we mentioned before, calibration algorithm must be redundant, so we should measure more data that needed to compute error terms. Based on this information redundancy, we can qualitatively verify the accuracy of the calibration results. The simple calibration algorithms like SOL for one-port cal or SOLT for the two-port cal do not allow such powerful calibration quality verification algorithms. So because there is no information redundancy acquired on calibration standards. What type of the approaches the engineers use to make sure that SOLT calibration algorithm was completed successfully? This is the measurement of the golden devices, or measurement of verification elements which were not involved into the calibration process, where we compare the corrected results versus expected results of one or another calibration standard and can conclude that our calibration was executed accurately. Calibration quality is acceptable. Calibria realizes this method. We call it reference verification. It means that verification of the calibration quality based on the measurements of the reference devices. Such reference devices can be located on wafer, or they also can be located on the calibration substrate. Let me show you how to enable this feature in Calibria and how to use it in a fully automated mode. So first of all, we switch to the map of our calibration substrate, and let us select few calibration elements to be our golden references. How to do that? We change the tool from move to the used for reference. That means that a particular element which we will select from the available elements from this map will be used as our golden verification. It's usually the element which we didn't measure multiple times, so brand new, I would say. And I would think that some of these elements can be used as a golden reference. So this one, this one, this one. So for instance, this through, this short, and say this open. Okay, the elements are marked as gold because they're supposed to be our golden reference elements, and they automatically appear in Calibria verification list. So this is the list of the verification elements, and it can be these elements can be measured right after we complete calibration process. You see, we will go to the open, we will go to the short, and we will go to the through standard after we complete the measurements of the calibration standards and compute error terms. So let us see how it all works in action. So we trigger calibration process. We measure calibration standards at first, so we move to our calibration standard, which is our through standard. We are somewhere here right now. We collect measurement data. Then we move to the load standard. We are over this load standard. As you see, we can live track the location and the calibration progress, not only through the Calibria graphical user interface, also through any other parts of Sentio related with the calibration process. Now we are over the map. So we are over this open element, and the last will be the short element, which is here. You see the marked as with a circle, red circle, means that this is an element that will be used for the calibration process. And the execution process is also showed here. We show the messages, what exactly is going on, like measuring calibration raw data, verifying the data repeatability. Then after the data compute, we compute error terms. We set error terms to the VNA, and now we start measuring our reference elements. You see, we are over the open reference element. This is here. Well, that's what we can monitor also from the execution list of Calibria. So we go over the open measurement. Then we move to the short, our golden reference short element. And the last element that we selected for such a verification is the through element. And let me give you an example of how to verify the quality of the calibration procedure, for instance, based on the measurement of the through standard. So the same user experience as you already learned from the execution of the calibration process. This is the standard, the data associated with the standard, our golden reference element. These are the raw data, but when we looked into the data measured for after the calibration process, we see some variations here. Let us go just one by one. Usually, when we looked into the data measured after the calibration process, we see a straight line, which is the model of our standard that we used for that, and these are the corrected data. So for the magnitude and as well as for the phase. And what is very clear to see here is that actually the phase, the model for the phase and the measured phase of the corrected data are very close to each other. And we can also look into the absolute error related to the measurements. For example, here we see that there is a little bit of error, maybe related to the drift of the instrument, which is about 1 degree at 67 gigahertz, which is literally nothing. We could set up the boundaries for this verification for the pass and fail criteria over the entire frequency range, and our boundaries, what we see here, are set up of about 1.1 degree of absolute error between the model and the measured results of the particular standard up to 67 gigahertz. And after we turn the analysis of the calibration quality, we see that results turn to the green and reference verification turn to the green, which means that we confirm that the calibration results are acceptable and we can move to the measurement of a device under test. By using this type of the calibration verification, we usually check the following parameters. This is the stability of our setup, drift of our internal setup, and also contact repeatability. If you want to qualify and make a full quantitative verification of the calibration accuracy, we must measure some specific elements, such as long transmission line, for instance, which models are also available from Calibria database. And based on these results, we will have a full understanding and qualification of the accuracy of the executed calibration process.